So, now what else is there to be found? We have to find the output resistance. Okay. That thing is the same for Thevenin and Norton. Essentially, what we have to do is we do not have any incremental input. Okay. We null the incremental input. The operating point will remain exactly the same, and we find the resistance looking back that way. Okay. What will that be in this case? What will it be? No, I mean in this circuit, I have not drawn any RDSs anywhere. What is it? 1 by GM of which one? Why? If you set I said Vd to be 0, right. So, what happens to this? What will be this voltage? 0. So, and what will be these currents? So, they will go away. Now, because there is no current here, what is the current in this? What is this current? 0. So, what is this voltage? 0 also, okay. And that 0 voltage is getting multiplied by GM. So, what is this current? Also 0. So, no current can flow here, okay. I mean, this is not very surprising. If I have modeled the transistor with only a GM and no GDS, what will be the Norton equivalent resistance? Infinite, okay. If I disable, if I set VGS to 0, this will go away and I will have infinite one. So, if there is no GDS for any of the transistors, the output resistance will be infinite, okay. The differential pair will behave like an ideal incremental current source, okay, controlled current source, that is all. So, again exactly the same as the transistor, except that you do not have gate and source which look different from each other. You have two inputs V1 and V2, the gates of M1 and M2. The output will be, I mean the equivalent will be just a voltage controlled current source of value GM1 times Vd, and the incremental resistance will be infinite, okay. And again, not surprising at all, if none of the transistors has an incremental output resistance, if each of them is a perfect control source, you can expect this type of result, okay. So, now obviously, this is not going to happen in reality. What happens if transistors have output resistances? So, we will have something GDS3, M3 and M4 are identical. So, I will call this also GDS3, okay, and M1 and M2 are identical. I will call this GDS1. What will be the output resistance or output conductance? Okay, you can calculate it, but again go step by step. First, imagine that only the PMOS transistors have a non-zero GDS. What will be the output resistance in that case? Yeah, output conductance will just be GDS3 because of this, all the other current sources will be off. Anyway, please calculate it and verify it. You can also try it with GDS1. It is actually substantially more messy, although the answer is very simple. Okay. Now, let us consider the other case where lambda n is not 0 and lambda p is 0. Okay. What will happen in this case? So, we will have GDS1 and GDS1 across them. Okay. So, now what will be the output conductance? What will the output conductance be? You can analyze it and see, it is a little cumbersome, but I mean it is amenable to regular circuit analysis. The important thing here is that these current sources are not inactive anymore. Okay. When you apply a test voltage, this voltage will not be 0, right. when you have this GDS1. So, you will get some value here and it turns out that it is very close to GDS1. Okay. The output conductance will be close to GDS1. You can take it as an exercise and do it for yourself and see. You will find some value. It will be slightly messy expression, but if you make some approximations, you will see that it is very close to GDS1. Okay. It is actually quite interesting to see how much current flows this way and how much current flows that way and so on. Okay. It is not that the current flows only downwards or upwards, there will be currents in every transistor. Now, if you have both lambda n and lambda p to be not 0, then again you can calculate the total output conductance. It will turn out to be close to GDS3 plus GDS1, okay, just like in a CMOS inverter, right. So, I will not go into the analysis of it, but you can take this as the small signal model of the differential pair for differential inputs. Okay. Is this fine? The small signal model, I mean, you can always use a Norton or Thevenin equivalent. In this case, the Norton equivalent is the easiest thing and it looks like a transistor, but with a differential input. Here I have only considered differential inputs, that is, I have assumed that plus half of the voltage is applied here and minus half is applied there and so on. Is it okay? So, the equivalent circuit is just a controlled current source in parallel with a conductance, again just like a transistor, right. What's that? Yeah, that is right. In this case, neither lambda n or lambda p is 0. Okay. I mean, if it is 0, that GDS will be 0. That is all. The expression is still correct. It is GDS1 plus GDS3. If lambda n happens to be 0, GDS1 will be 0. That is all. Okay. So, you have to calculate the GDS value from the lambda and the bias current that is flowing in the transistor. Any questions about this? So, again you please derive this for yourselves, and when you see a differential pair, in most cases you should be, and if it has differential inputs like this, you should be able to use this model. Okay. Any questions here? Okay. So, this is the model that we use for most often for the differential pair by itself.